quick question. How many people have read like the intro to experiment 20? Okay, so there's that little hypothetical thing about this case study that we're going to do. I thought I'd try and introduce this a slightly different way. Okay, so bear with me if this doesn't work, but I thought I'd give this a try. So much better than the first page, right? Now let's go do some chemistry. All right. So now back to the more familiar nuts and bolts. All right. This is the plan for what's going to go on the next couple of weeks. All right. So I'll show you kind of the overview, and then we'll get down to the nuts and bolts of what we'll do this week. Okay. All right. So those potential antifungal compounds that were referenced there in the nifty little opening. Okay, so these are those hypothetical compounds right here. Okay, so the theory is if you can get a hold of one of these, it could be the next big thing. The problem comes, however, is you can't get these directly. Okay, and pretend that they're not terribly easy to synthesize, which to be honest, those compounds aren't. Okay, but you could easily make them from one of these compounds. Okay, so this happens at times in the pharmaceutical industry where you can get like bucket loads of one compound, but it's not quite what you want. It's something closely related to what you do want. Okay, and in this case, based on the theory there in the lab manual, is we can get a hold of a lot of these diesters here. So note there's an ester up on the top and an ester on the bottom from each of these. Those are a great source of this compound if we can find a way to selectively cleave one of those esters over the other. It turns out chemically, something like this can be really pretty challenging because they're both esters. And how do we get something specific that it'll do one and not the other one? Okay? And so that's ultimately what we're going to try to do over the next 3 weeks is make a bunch of compounds that sort of look like these and then test some esters to see if they're selective in the way that we want them to be. Okay? All right, and the catch is that we can't use these compounds directly or we don't want to. In the pharmaceutical industry, it may be because we don't want to hack down an entire forest of trees in order to get that little bit of compound that we may or may not be able to successfully convert. So what we do is we make model compounds, ones that are much simpler, easy to get a hold of. We test out our conditions, and then once we've got good conditions, we then go back to try it on the real thing. Okay? And so that's what we're going to do over the next weeks is make those model compounds and test them. All right. And so the general idea of making these model compounds, okay, we're going to make a bunch of model compounds that look like this. So diesters, okay, they're going to have an alkyl group on one side and an alkyl group on the other side. How we're going to do that? So in experiment 20A, so what we'll be doing this week, okay, we'll be doing what's called a Fischer Esterification reaction, and I'll go into the nuts and bolts on how that thing works in a few minutes. But ultimately, we'll take these hydroxybenzoic acids. Okay, everybody's going to start with the same hydroxybenzoic acid. Okay, and we'll split you into groups, and ultimately, a third of you will use methanol. So this R prime here is the methyl group. A third will use ethanol, and a third will use propanol to make 3 different esters like this. Okay, so that'll be what we'll do this week. Okay, we'll purify those, etc., identify, make sure that you've got what you want. Okay, next week, then what we do is we put the ester on the other side. Okay, and so this is what's an alcoholysis reaction of an acid chloride. Okay, that'll be next week. And so now that open OH on the material that you make this week next week that will react with the acid chloride. Okay, so that'll make the diester up there. Okay, so now at this point, being that we're going to start with 3 different alcohols in the first step, we'll use 3 different acid halides, acid chlorides in the second step. Now that'll make a library of 9 different compounds. Okay, all of these are different possibilities. By the way, all of these are in your lab manual, so you don't need to feverishly scratch everything out. Okay, so between a lab section, you'll make all 9 of these, and then there's going to be 2 enzymes that we have that cleave in different fashions. And then your job ultimately is to, you individually will make one of these 9 and test one enzyme. And then collectively in your section, you'll get the data from all 9 of these and the 2 enzymes, 18 different reaction conditions. And then you'll basically look at that whole shebang, okay, and determine which ones work how well. Okay? All right. Once you get a hold of all those model compounds, like I said, we're going to do the enzymatic hydrolysis, so that'll be 20C. Okay? For some of you, it'll be your last ever organic lab. Okay, so we don't know how well tears catalyze this reaction. Maybe we can figure that out. Okay? All right, but ultimately, the 2 enzymes that we use are pig liver esterase and orange peel esterase. Okay, so each of those, luckily, we'll make it from the orange peel. Luckily, we can just buy the pig liver. We don't have to make it from pigs. Okay? But we try those 2 esters, and there's 4 possible outcomes of this reaction. So you can put in your starting material, you can get starting material back out. Okay? We can get hydrolysis of both esters is a possible outcome. Okay? And then we can get selective hydrolysis of, say in this case, the right-hand side, or selective hydrolysis of the left-hand side. And as you'll find out, you can get a mixture of these, right? So it's not going to be clean, or at least most of them are not going to be clean 100% product A or product B or product C. Okay? But that's your job ultimately, is to figure out with the compound that you started with and the enzymatic conditions, which of these do you get, what's the ratio between them, and so on and so forth. Okay? Ultimately, your job then over the course of the next 3 weeks as a class, luckily instead of having to make all 9 of these compounds yourself and run both enzymes yourself, we're going to do this as a class as a whole. You're going to prepare 1 model compound. You're going to perform the hydrolysis. Okay? You're going to analyze both your data first to figure out which of these that you get. Then you're going to analyze the class data as well. And then ultimately determine which conditions to use to obtain that desired product. Okay? Ultimately, I personally, for my section, I'm a little bit more interested in, can you tell me how, what's the separation, which ones work well, which ones don't, kind of general ideas about how those enzymes work, and a little less about which ones give you this specific product. But ultimately, if you look back at that case study, the idea is which of those conditions will give you this species right there. Okay? So any questions with the general kind of overview? This is what we're going to do over the next 3 weeks in lab. So 20A, B, and C, making those compounds, and then doing the enzymatic hydrolysis. All right. Okay, each of you, I think most lab professors have distributed technician assignments. If not, you will get those soon. So those of you in Stanford's class tomorrow morning have them, correct? Okay, good. So you know what to do there. All right, so this is ultimately it. There's 18 different combinations. Okay, so your R prime is the alcohol you use in step A. The R is the acid chloride that we'll use in step B. Okay, and then finally your enzyme in step C. So you can see based on which one you have, you'll be able to see what you're going to look forward to over the course of the next few weeks. Okay? All right. One thing I'll note, for each part, your pre-lab will only have to deal with the specific conditions that you use. Okay, so for this next time, for example, no need to look up all 3 different reaction conditions and the products and everything else. Okay, you should do the calculations that you need for simply your alcohol that you're going to use, and then determine the theoretical yield for your product that you expect to get. Okay, no need to worry about what anybody else is going to get, just use yours. So pick one of these alcohols, whichever, based on the technician number, okay, and then do the calculation specific for yours. All right. Questions so far? All right. Has whose afternoon section gotten your assignments? Yep. Yes. All right. Anybody not have their assignment? If you haven't, you probably check your email, because I sent mine out this morning. So, all right. If you have any troubles, let me know and we can track those down. All right, so the reaction that we're going to do this week is called the Fischer Esterification. Okay, we'll cover this in lecture here in probably about 3 or 4 weeks. All right, the general reaction that's happening is you have a carboxylic acid that you're starting with. Okay, so I've highlighted that, at least the part that's going to change here in green. You add in an alcohol, just a couple of drops worth of a sulfuric acid catalyst. And ultimately what you'll get is that ester, this acid will be converted into an ester. And then the byproduct in that reaction is water. All right, so I'm going to walk through the mechanism here. First of all, it's a Fischer esterification. Give a little shout out to Emil Fischer. This is one of the granddaddies of organic chemistry. So we'll see him again later on in this semester quite a bit. You see really a stylish guy up there. And was awarded actually like the 2nd ever Nobel Prize in chemistry back in the early 1900s there. So obviously this is named after him for discovering the reaction. And so how does this work? Okay, so the mechanism, so no need again to feverishly scratch everything down. I'll walk through it. The mechanism is on page 20-4 of your lab manual. But just to kind of walk through the ideas on it. Okay, so the the carbonyl here, sorry the arrow doesn't quite match up, reaches out to grab that hydrogen off of your acid catalyst. Okay, so you'll protonate that carbonyl, and it'll give you this species right here. Okay, what does that protonation on the carbonyl do to the electrophilicity of that carbon of the carbonyl? Does it make it more electron rich or less electron rich? Okay, I think you mean it's less electron rich, right? It's pulling electrons away from the carbonyl carbon. So there's now a formal positive charge up here. Those electrons are being pulled up towards the oxygen. Okay? As a result, it's easier to attack that carbon now. Okay? And so what happens then is one of the molecules of the alcohol there comes in. It attacks that carbonyl and kicks the electrons up. Okay? Same general idea what we see with a Grignard reaction, where something with electrons comes in, attacks the carbonyl carbon, kicks those electrons up to the oxygen. Okay? Now, however, that gives us this tetrahedral intermediate that looks like this. Okay? Obviously, we're not done yet. In, say, a Grignard that we've seen before, that's where it stops. But ultimately here, we need to get rid of that green OH that I've drawn in there. And so what happens is one of these protons gets grabbed by that oxygen. So these lone pair on the oxygen comes and grabs that hydrogen off, pushes the electrons back onto that oxygen. And so now you've simply transferred that proton from one oxygen to the other one. Okay, so that species looks like this. So now what happens is you've now created a new good leaving group, right? So this is now a positively charged group. It's pretty easy. That thing's going to leave. It's going to leave as water. So that's pretty easy to happen. What happens is one of these oxygens here with the lone pair pushes the electrons down and kicks that oxygen out, okay, the water molecule out of the molecule, giving you a protonated carbonyl. And then now that protonated carbonyl just leaves the electrons behind. Okay? Or you can see the water molecule, that catalyst that you started with at the beginning. Okay? You pull off the hydrogen, kick the electrons down, you regenerate that catalyst. One thing you'll notice, you look around this, every one has these double-headed arrows. What does that mean? All of these steps. Well, not double-headed arrows, the 2 arrows, one going back and one going in each direction. What do those mean? Okay, it's reversible. It's an equilibrium. Okay? Every single step in here is an equilibrium. Okay? How do we actually get the product that we want if everyone goes back and forth? How do we drive that equilibrium? Okay, heating and cooling will simply catalyze the reaction, make it go faster or slower, do a tiny little bit on equilibrium. What do you got, George? Concentrations of stuff. Okay? In which particular direction do we want to push it? We want to go this way, so what concentrations of stuff do we change? Okay, if we can pull out the oxygen, or the water, it will push it or pull it to the right. Otherwise, on this side, I have it above the arrow, but the alcohol lies on this side of the arrow. If I dump in more alcohol, it's going to push that to the right. Okay? That's why for this reaction, what we do is we run this as alcohol as the solvent. Okay? So all steps are reversible. You have to use the liquid alcohol as your solvent because that's ultimately what drives the equilibrium. Okay? You can, on the other hand, in certain cases, use a method of pulling that water out. Okay, that tends to be more difficult. Okay, but what we can do is just swamp it with alcohol. Okay, so because we're running this in an alcohol solvent, whether it be methanol, ethanol, or propanol, okay, then the concentration of those is going to be really quite high. That's going to drive this reaction to the right and give us totally the ester there. Okay. And as mentioned, the acid is a catalyst. Okay, so that just makes that reaction go a little bit faster if you add that acid catalyst in. All right. Any questions with the mechanism or how we push that equilibrium back and forth? Okay, so at the end of the day, if you don't take that water out of the reaction, or if you put extra water in there while the acid is still present, what's going to happen? Okay, you're going to reverse the equilibrium. You're going to push it back towards the product. So remember that. You don't want to add water to this reaction before you get the acid out of there. Okay? Once that acid catalyst is gone, then the products become really quite stable. All right. Okay, so some hints and tips and odds and ends for actually doing the reactions. Okay, as I mentioned before, you'll be assigned one of these R prime groups based on your technician number, so be sure you pay attention to that. Okay, so the R prime there, if you just have one carbon, it's methanol, 2 is ethanol, 3 is propanol. Okay, so be sure you note those. These are pretty straightforward. The R's next week aren't quite as intuitive in terms of naming, so we'll see that next time. Okay. Ultimately, this reaction requires a 2-hour reflux. Okay, it's a relatively slow reaction, so we gotta, even though we have the equilibrium is going to push it pretty good to the products, we let it go for a couple of hours to make sure things go. Okay, we'll use a heating mantle. Okay, it's a reflux. Okay, so typically, based on your boiling point of your alcohol, those reflux temperatures are going to be a little different. We'll just make sure we get there by using the heating mantle. The general approach that we'll use this week is to get to lab, get started setting it up. Once everybody's refluxing, then we'll deal with the quiz. Then we'll deal with any pre-lab hints and tips on the workup process. Okay, so ultimately, get ready to get there right at the time your lab starts and dive in and get that thing set up. And then we'll take the quiz and deal with that sort of stuff after everybody's ever refluxed. Okay? It's a little bit better time management. All right, questions on that so far? All right. Okay, once you do that reflux, so a couple of hours later, depending on which alcohol you're using, okay, methanol and ethanol are removed by distillation. Okay, so you'll want to use a hot water bath there instead of a heating mantle because you don't want to scorch your product. Okay, so go ahead and use a hot water bath to distill off the ethanol and methanol. Okay, you might be disappointed that you don't get to use a rotovac, but I promise you that especially in the sections that have 2 sections going on, that there's going to be a longer wait for rotovac versus just distilling your product off. So, okay, so you go ahead and remove those by distillation. For the propanol, that's a tougher one to do by distillation just because of the temperature involved, and we have to go to a heating mantle instead, and there's other risks. So what we do is we go ahead and just use a rotovac for those. So if you're using propanol, we'll rotovac those off. And you may be smiling about that now, but sometimes it can be difficult even with a rotovac to get that propanol off. So we'll see what happens come Tuesday and Thursday. All right, following the removal of the solvent. Okay, so you get rid of all that alcohol then. There's a series of workup steps. All right, so you'll have a little residue that's left there. Okay, so you'll get rid of at least most of the alcohol. You might have a little bit left. There'll be some residue. That's going to be your product or your crude product with some other stuff left in it. Okay, you dissolve that residue in ether. And once you do that, we do have a whole series of extractions and washes right now. Okay, so your product is dissolved in the ether. Okay, you wash it twice with 25 mils of water. What's the difference between a wash and an extraction? In general, it's a wash if you have your product in one layer, either aqueous or organic, one phase. You put something in and take that same thing out, and your product stays in the same layer that it started in. That's generally a wash. Right? You have it there, you put something on it, you take that off, and you still have it where it was. That's a wash. It's an extraction if it's in one layer, and then you move it into the different layer. Okay? Or take it from a solid to a solution like we did in experiment 3, things like that. So it's changing phases or layers, then that's an extraction. In this case, it's a wash. Okay, so it'll stay in the ether layer. This is always the nice one because you'll have an organic layer, you'll put water in, you'll shake it, the aqueous stays on the bottom, you can take it out, and your organic layer is still there and you can continue moving forward. Okay. I would give you the advice now, be sure you label things carefully and don't throw things down the sink until you're absolutely sure that you know what it is and where your product is. Okay, because once your product goes down that sink, it's hard to get it back, and you'll be refluxing for another 2 hours. Okay, nobody wants that. All right, that's right. I can hear the excitement about that prospect. Okay, so you wash it twice with water. Then you wash it once with a sodium bicarb solution. So we put a little bit of a weak base in there. Then you wash it once with 25 mils of a brine solution. This is like a witch's brew here. Okay. After that, you've got your ether layer. Then you dry it with magnesium sulfate. Okay. You can rinse it well with ether as you filter it into a tiered flask. Okay. It's a good habit to get into, to always tier your flasks, especially if they're round bottoms that are headed into the rotovap. Okay. But be sure you tier this one. It's going to make your life a lot easier. All right, so now the question, what is each of these steps for? Why are we doing this kind of random assortment of steps? Okay. All right, so we dissolve it in ether. Okay, that's right. We get it into the organic phase. That's not too bad. The first step here, we're getting rid of the solvent. Okay, we're putting it into a solvent that's a little easier to deal with. Alcohols are messy. Okay, if there's too much alcohol there, you know how, like, especially methanol, it's sort of like water with the OH, and it's sort of like an organic with the CH3. The problem is if you try to do an extraction or something with an alcohol like that, it kind of becomes a little bit of both, and often you can get just one layer instead of 2 nice layers of an aqueous and an organic. So what we do is just to eliminate those problems, we get rid of the alcohol. Okay, so that's what happens in the first step. Okay, so we dissolve it in ether. What does washing it with water do for us? What are we going to get out of this reaction mixture? Okay, think of what's left in there. We got a little bit of acid that might go in there. If we have a little bit more alcohol, the alcohol probably will go in there a little bit. Okay, there's some salts that can be left in there. We'll get rid of those. Okay, this sodium bicarb. Okay, that's the one that's going to get, if there is any sulfuric acid still left in there that didn't get out in that first wash. Okay, that'll get rid of any last little bits of that sulfuric acid. It'll neutralize that, give us some salt that'll then dissolve in the organic layer. Okay. One thing that's worth noting, we don't do that necessarily first, because if there is quite a bit of sulfuric acid there, as soon as you hit it with bicarb, that's like the volcano that you made as a kid, right? It'll go right out the top of your set funnel. So sometimes it's useful to kind of get a lot of that sulfuric acid out with just water, okay? Especially when there's not a whole lot of it there. All right, so then we use this to get rid of any last traces of that acid. Okay, what about the brine? What does the brine wash do? This will actually pull out little bits of the last little bits of water that are in there. So if you still have some water that's in your organic solution, so essentially this is an osmosis type thing, right? So that it'll go into the water layer to try and further dilute your saturated sodium chloride. So you're going to remove residual water from your organic layer. It'll go from the organic layer into the aqueous layer. And then finally, we're familiar already with magnesium sulfate. Okay, so hopefully by that time you can't see any water in your organic layer. If you can see any water, then you're going to want to try some of these other steps, probably that brine wash again. Okay, as long as you can't see any water in your flask, go ahead and add in a bunch of magnesium sulfate. That'll dry it, and from there you filter it, and you should have a nice dry ether solution in your tiered flask. Okay. All right, any questions with that sequence, sort of what those are for? And so these are the highlights, some of those, that rationale.
So we don't do that in GSO4 in our separatory funnel, do we?
No. Yeah, take that back out. Yeah, learn all of the things that you remember from the first semester, right? And then we're just kind of adding in a little bit here and there. But yeah, ultimately, once you've done all of your washes, you take that, you put it into an Erlenmeyer is always the best one to use for a drying step like that, and then do the drying in there, and then filter. Okay. And again, rinse well with ether, because what's ultimately going to happen is rinsing it with ether will get all of your product off with magnesium sulfate and so on, and then ultimately you're just going to rotovap off the ether and be left with your solid product. So ether is pretty much just a vehicle to transfer it from one thing to another. All right, now with your ether solution, you want to rotovap it. Okay, you're all pros at rotovap now. You want to put it on the high vac. You're all pros at the high vac now, and then you want to get set up for an NMR. Okay. Last little things you do with your residue and things you have it in a tiered flask already, so all you have to do is make sure it's all dried off after the rotovap, and if it hasn't dried off sitting on the high vac, Make sure it's all dried off, put it on the balance, voila, you've got your yield. Okay. From that, you want to remove about 100 milligrams or so for a TLC standard next week. We'll try to remind you of that again next week to make sure that you don't bust forward without that. You want to make an NMR sample. These products, I think most of them are oils. There's one of them that might be a solid depending on exactly how you do it. Okay? But you go ahead and make it, regardless of what it is, make an NMR sample. Pretty straightforward, and obtain an IR of your product here. Okay, I can't really emphasize this enough. So you're going to have two different things. You're going to have one, probably a round bottom that has your product in it. You'll have one vial that has about 100 milligrams in it. Be sure you label them clearly and store them in a safe place because we're going to need those for the next 2 weeks of experiments. Okay, so use those Sharpies. All right, for the write-up. Okay, any questions on that so far in terms of the final things and what you need? NMR, IR, a little bit set aside. Again, all these things are labeled in the lab manual, but I figure if I tell you and then your lab rep will tell you and you read it, then most of you will remember. All right. Okay, here's like the little catch for this. Because this is now your starting material for 20B, we need to make sure that you made what you think you made and it's in good shape that you can actually use it next week. All right, so there's a little bit of an accelerated timeline here for looking at things and processing data and so on. All right? So here's what you have to do before next week, okay, is to process your NMR at your earliest convenience. Okay, complete the NMR data table. Okay, include impurities in there. Okay, so if you have a significant amount of any impurities, please include that in your NMR data table. Okay, and just, under the notes section, you can just identify whatever it is. Okay, analyze your IR spectrum. Okay, and complete an IR data table. And then attach these items to the worksheet. And then the worksheet is on page 20-13. Okay, note that it's at the end of the section in your lab manual. It's not right where it would kind of make sense to be at the end of 20A. It's tucked at the end. Okay, and that worksheet's going to look like this. Okay, it's another one of these nice little worksheets that's pretty straightforward to complete. All right, some of the highlights in here you can go through in detail and take a look, but ultimately these first two have to do with the IR. Okay, so to take a look at the IR, make sure that it matches what you think you should have at this stage. The other thing we'll ask you to do is to compare it to the starting material. Okay, one of the ways to tell that something has happened here, right, is that it is possible, and I have to say I've done it way too many times. You try some new reaction, you work it up, you get this product in your hand, you're assuming it's the product. If you take a couple seconds and look back, sometimes it's exactly the same as your starting material. Okay, hopefully that won't happen to you, but it's a great way to check to make sure that some reaction has happened. Okay, so you want to compare that to the starting material, okay, and then basically attach it to this form. Second part is to do the analysis of the proton NMR spectrum. Okay, use your guide and expected your starting material, right, and your expected product as your guide when interpreting that. So hopefully that should be relatively straightforward. Okay, so we put that, and again attach the spectrum and include any unknowns in there. Again, on your spectrum, be sure you draw your product out and then label all the peaks, A, B, C, D, etc. Okay, and label those as best you can on the spectrum itself. So both on your compound and correlate them to the spectrum. One thing I would say is in terms of what do you need to include, this also goes for 17, I'll talk about that a little bit more in a second. Include only the spectra that you really need to prove your point. Okay, there's nobody gets awards for putting the most blow-ups of their NMR spectrum in their lab report. Okay, so go ahead, if it's one and it's straightforward, go ahead and do that. If there's something you have a question about or you really want to bring attention to, go ahead and put in a couple of blow-ups. Okay, but just use, don't just randomly print things out and staple them in there. Okay, it drives everybody crazy. So, all right, and then basically the last thing here is pretty much, is there anything, are there any extra peaks in your IR? And ultimately the last one that isn't on this that I put there, is there any reason not to continue? Okay, so is there anything that worries you that you shouldn't go ahead? And I would tell you that for pretty much everybody, you should not have any problems at this stage. This is relatively straightforward. If you do have any issues on something that's a little weird or unexpected, go ahead and bring that to the attention of your lab instructor. But this one, should go pretty nicely. Okay? All right, and this is the important part. This report is due relatively quickly. Okay? Because we have to turn this around, we have to check it, make sure everything is okay. Those of you doing this lab tomorrow have to interpret your IR and your NMR and write up this little sheet, okay, due by Friday of this week. Right? And then those of you who have lab on Thursday, they have to do it do that analysis, and it's due next Tuesday. So ultimately, we can take a look at it and say, okay, yeah, you're A-okay to do it next Tuesday. Right? So again, and especially because of the quick turnaround, we don't expect, you know, large, drawn-out conclusions and anything else. This is pretty much just straight data analysis. What's in there? Is it what you think it is? Done, going forward. Okay? Any questions on that?
So we don't need to do an additional one-page write-up, it's just fill that sheet out with the data.
Fill that sheet out. That's it. Okay? Everybody likes worksheets, so it's kind of a toss-up. It's a short deadline, but it's just a worksheet. All right, couple other things. You'll submit the worksheet for 28, but in your notebook. Here's a couple of things to be sure you have in your notebook. Your pre-lab, okay, that's hopefully that's old hat by now. Okay, your experimental, also old hat by now. Then the last thing is once you've looked at all your data, and yep, it looks good, there might be, okay, there's a little bit of ether still in my reaction, but otherwise it looks like I made the product and it's nice and clean. Just write a quick little one-paragraph conclusion on 28. So right at the very end, basically write that thing up. I got my desired product, it matches the NMR, it matches the IR, and I have it in 75% yield. I'm ready to go for 20B. Okay, so quick little, literally 2-3 sentences is all you need. That just confirms that you've looked at your data and it looks good to go forward. Okay, and so that's in your notebook. Okay, any questions with that? Yeah.
For the pre-lab that's due tomorrow, just for 20A.
Just for 28. Yeah, we'll take them one chunk at a time in terms of the pre-lab. Yeah. All right, any questions with that? All right. Okay, and again, don't forget, it's going to be due this week. It's a fast turnaround. Okay, overall, thinking about, okay, so this is the game plan, we talked about this. Keep in mind that those are due this week or early next. The other thing to keep in mind, okay, so you actually have a week. It's going to get weird because you need to give us back 20A. 17 is still hanging out there. All of your NMRs from the VIDIC are all done. They're all ready for you to go and process them and work through and do all that analysis. I'd suggest doing that sooner rather than later. Okay? Ultimately, those aren't due until next week yet. So it's one of these weird situations. It would be great for all of you to get your pre-labs done right now, then to go and get 17 done, submit it, or at least hang on to it, and then you don't have to worry about it anymore, but I know you won't do that. Okay? I know the truth. Okay? But then you'll have to do 28 and then go back to 17, right? And kind of go back and forth. Okay? So 17, I will tell you, is a full report. Okay? So keep that in mind. That will include an introduction and a background and the data analysis and everything else. Okay? So as you know, I know as well as you do, those things are beasts. So don't wait too long to get on that. But those things are ready to go. Get that NMR processed. You will undoubtedly have questions in terms of interpreting and things, so it's always easier to ask those questions now rather than, you know, Wednesday night of next week when it's due in 12 hours or whatever. So, all right, any questions with anything? Yeah, no.
So from last week's experiments, I read that you can't use 100 milliliters of bottom flask. I was wondering what the acetone would cause to the reaction.
Oh, in this one?
Yeah.
That's a good question. It's just the fact that you need to use it right away next week.
Okay.
Yeah. So there's a question on. There's a little note in the experimental last week about the round bottom flask. Don't use the 100 ml round bottom flask for collecting the VIDIC product. Okay. The reason is we want to use that 100 ml round bottom flask this week. Okay. If you happen to use it, and you know that's okay. Okay. We need the heating mantle. That's the key. So we need that one. So I would just say that if you do have your VIDIC product in that one, you're probably going to have to take your VIDIC product and transfer it into a different flask, okay, and then use that 100 ml round bottom just because it fits nicely in the heating mantles and so on. So that's just nothing terribly wrong with it. A little bit of acetone in that reaction won't hurt it in the Fischer Esterification. It's just the fact that you have to take that and transfer it into something else. Okay. One great thing to do is if you haven't done it already, if you pull up your VIDIC NMR and look at it and make sure that it's clean and nice, which I could say all the ones that I've looked at have looked really good so far, but take a look at them, and then in that case, you don't have to be as careful about saving your VIDIC product. Assuming that your NMR looks really good of your VIDIC product, you don't need it anymore. Okay? So it's nice to have it just in case something goes wrong and you need to take another NMR or something, but if you've got a good NMR, you're set to go. All right, other questions? to say if there aren't other questions, you're free to go now. You've got 15 minutes to go work up that NMR. So go make it happen. If you got any questions, come